So in the last class we were discussing the properties of the exponential of a tensor, and we saw that if e to the a plus b times xi is equal to e to the a xi e to the b xi for all xi, then we had that a b is equal to b times a. I am suppressing that argument t because that is not really required. We just need this argument of xi in this particular result. And then we also showed that conversely, if a b is equal to b a, then e to the a plus b times xi is equal to e to the a xi e to the b xi, which is also equal to e to the b xi e to the a xi. Okay, so we have seen this result. So if you choose now xi equal to 1 in this particular result here, so choose xi equal to 1, then in that particular case we will see that if ab is equal to ba, then e to the a plus b is equal to e to the a e to the b, which is also equal to e to the b e to the a. So from this particular result here. So let me just write that here. So if yes, so if we take now this xi to be 1, then AB is equal to dA implies that e to the a plus b is equal to e to the a e to the b, which is also equal to e to the b e to the a. Okay. So we have to be very careful in the way we use this particular result here. So I already pointed out, when you have for numbers, we don't have to really bother because e to the x plus y is equal to e to the x e to the y, which is also equal to e to the y e to the x. So when we are dealing with the space of real numbers, then this result will trivially follow. But here we need AB to commute with BA in order for this particular result to hold. So in particular, now if AB is not equal to BA, then this result may not hold. Okay, so let me just discuss the various possibilities that can exist. So if AB is not equal to BA, right, then in that particular case one can have e to the a plus b is equal to e to the a, which is equal to e to the b, which is equal to e to the a e to the b. Okay, or we can have so let me write out all the possibilities here. Or we can have e to the a e to the b is equal to e to the a plus b, which is not equal to e to the b e to the a. Or you can have another possibility, which is e to the a e to the b is equal to e to the b e to the a, which is not equal to e to the a plus b. Okay, so you can see that there are all kinds of different possibilities that can exist if you have that AB, and if suppose AB and BA do not commute, then you can have all these kinds of possibilities that whatever I have listed here. So one has to be really careful. So it is not as trivial as the case of real numbers where just e to the x plus y is always e to the x into e to the y. So here, as I said, that if A and B do not commute, then you can run into a problem because all these various types of possibilities can exist. But if AB is BA, then we can definitely say that e to the a plus b is e to the a to the b is just equal to e to the b into e to the a. So we will look at a very nice application of this particular result now to show the inverse now of an exponential tensor. So if you go back to the basic definition, right, then you'll see that finding the inverse is not going to be a very trivial problem, right? Because you have e to the a is I plus a square by 2 factorial plus so on up to infinity. So you can see that to find the inverse of this is definitely not a trivial task, right? If you try to do it just using this infinite series, then definitely it does not look possible. So we will use this particular result to show to find out the inverse of an exponential tensor. So here, since now t and minus t commute, so we have that. So let us look at this particular result here. So now we will have that take a to be t and take b to be minus t. So take a, you identify with t, and b you identify with minus t. Then in that particular case, you will get that e to the t minus t, which is equal to e to the 0, which is equal to identity, which is equal to now you have sorry, so we are using this particular result. I'm sorry about that. We are using this particular result here. So now we will have that e to the a plus b is e to the t minus t. So this is a plus b here. So yeah, e to the t minus t is e to the 0, which is identity, and that is now equal to e to the t times e to the minus t, and also equal to e to the minus t times e to the t. Okay. So now we can see that because you get the identity tensor here, so this object must be the inverse of e to the t. So this implies now, that e to the t inverse is equal to e to the minus t. That is what now we have shown here. Right? So this is a very nice and elegant result. So you can see that basically what you need to do is that you just need to put wherever t occurs, you need to put minus t. That's all. So suppose this was e to the t, that is equal to I plus t square by 2 factorial and so on. So e to the t inverse would be I minus t plus t square by 2 factorial and so on, minus something. So that is how you would get e to the t inverse. So simply replace t by minus t and find e to the minus t, and then that would be the inverse of e to the t itself. So as I said, very nice result using this particular property here. Fine. Now let us proceed. So what about e to the w of t, where w is a skew symmetric tensor? So let us look at that now. Yes. So theorem. So let w of t belong to skew, okay. And for all t, then e to the w of t belongs to R plus. Again, very nice result for each t greater than or equal to 0. Okay. So proof of this. So we want to show that the transpose is equal to the inverse, correct? That's what we want to show because it's an orthogonal tensor. So first let us find out what is the inverse of this. So by the previous result, now we can write that e to the w inverse is e to the minus w of t, and this is equal to e to the w transpose of t, because transpose will be minus of w because it's a skew symmetric tensor, and we have seen that this is e to the t of e to the w of t the whole transpose, right? Because this result also we have seen that e to the a transpose is equal to e to the a the whole transpose. So this we have already seen this particular result, so we are using this. So what we have shown is that the inverse of e to the wt is equal to the transpose of e to the w t. So hence, since the transpose is equal to the inverse. Hence, it's a orthogonal tensor. And in one previous class, we have seen that the determinant of e to the wt is nothing but e to the trace of w, which is e to the 0, which is equal to +1, and hence it's a proper orthogonal tensor. And so that is just show that. So determinant of e to the w of t is equal to e to the trace of w of t, which is equal to e to the 0, which is equal to +1. So hence e to the w of t belongs to orth plus, as is claimed here. Fine. So so our interest again mostly is in the three-dimensional case. So in the three-dimensional case, this e to the w of t can be given a very nice explicit formula, which is known as the Rodrigues formula. So let us look at that formula now. So in 3D now, in 3D, so basically we will use the Cayley-Hamilton theorem. Okay, so by the Cayley-Hamilton theorem, we have w cube of t is equal to minus w of t square times w of t. So this small w is the axial vector of the skew symmetric tensor capital W, and this is nothing but the norm of that axial vector w of t here. So this actually follows because the first invariant of w, which is the trace, is 0. The third invariant, which is the determinant, is also 0, and only the second invariant is a non-zero quantity. And then using that and the Cayley-Hamilton theorem, we get this particular result. Then from this we can get higher powers of w. So now w raised to 4 of t can be written as minus of w of t square times w square of t. And then similarly you can go ahead, I mean you can keep finding all the higher powers. So w raised to 5 of t is equal to w of t raised to 4 times w, and so on. So okay, so basically you will see that all the powers, right, all the powers higher than 3 can be expressed either in terms of w or w square, because so you keep on repeating this process, and then finally you substitute all of this into the infinite series, right? E to the w of t is equal to I plus w of t plus w of t square divided by 2 factorial plus and so on. And so once you substitute that into this expression here, then what you will get is the following. So you will get that r of t is e to the w of t. So I'm just calling this e to the w t as a rotation r of t. This is equal to I plus sine of w of t, sine of w of t divided by norm of w of t times w plus 1 minus cos of w of t divided by w of t square times w square of t. So this is a very nice and elegant formula that you get for e to the w of t. So this is valid only in, of course, in 3 dimensions. Okay. So you can derive, I mean even in higher dimensions we can derive it, but for our purposes this is good enough. So here maybe you can put on brackets here, 1 minus cos of w of t. So you can see that this formula is very similar to what we had derived earlier, right, where we had this representation with a sign alpha. This alpha is just w of t basically. So at that time it was not clear how I had obtained that particular representation, right? I had I plus sine alpha divided by the norm of this w of t times w and 1 minus cos alpha and so on. So now it is clear from where I got that particular representation, because so basically it is just the exponential of a skew symmetric tensor. So that is the way I had obtained that particular representation. Okay, so this exponential of a tensor will play a key role at a later stage. So that is the reason that I covered this. But for now, we will just move on to the next topic. So now we will just consider various theorems such as the divergence theorem and so on, which will again play a very key role in deriving the balance laws, because see, the balance laws are all in integral form, and to convert all of them into partial differential equations, we will need the Gauss divergence theorem. So anyway, to that part, again the application part we will come to at a later stage, but right now let me just state what the divergence theorem and Stokes theorem and so on, the various theorems, let me just state them right now. So we will not prove these theorems, proofs are fairly complicated, but I will just state these particular theorems here. So divergence theorem, so also known as the Gauss theorem. Theorem. So here, if we have if phi is a scalar, phi is a scalar valued field variable. So you can think of phi as let's say the temperature or the density or something like that. Then integral of del phi dv over v is equal to integral of phi of n times ds over s. So here v is the domain. Let's say v is this particular domain, s is the surface of that particular domain, and n is the normal to the unit normal at any point on that particular surface. So there is an integration involved over the entire surface. So this del phi times dv is phi times n. Yeah, so this actually I will give a sort of recipe now for doing this kind of a for getting this particular result here. So the recipe, so remember that it's a recipe, it's not a proof of the theorem. So just basically the rule is that del by del xi goes to ni. So you should remember this particular rule here. So here, for example, del phi, the ith component of that is del phi by del xi, right? And then that goes to phi times ni, right? And so phi times ni, so that is actually just the component form of phi times n times d. So we will use this particular sort of recipe. As I said, that this is not a proof, this is just a way of remembering the result, a mnemonic if you want to call it that. So let us just derive various kinds of other results from this recipe here. So this del dot u times dv, so this is actually u dot n times d over s, so this is over v. So here you can see that del dot u can be written as del ui by del xi, correct? And then that goes to ui ni, correct? Because the del by del xi goes to ni. So ui ni is nothing but u dot n. Okay, so in this particular way we can derive it for any number of different types of identities. We can derive it in this particular way. So now let me look at another del u times dv. So that is equal to u dyadic n times d. So again, if we go back to this particular recipe, this del u has the components del ui by del xj, and then that goes to ui nj. Right? And then that is nothing but the component form of u dyadic n. Right? So that's so that is how we get this particular result. Then similarly, del dot t times dv is equal to integral of t times n times dx. Okay, so this also same way. So this del dot t, so del dot t, the ith component of that is del tij by del xj, correct? And this del by del xj goes to nj. So this goes to tij nj, correct? And then from that, this is nothing but the component form of t times n. So I think you get the idea from this that we can generate. So basically, if you remember this particular rule here, which I have put in this box, then I think you will be able to derive similar kind of results for other types of quantities also. And this result is valid even in 2D also. Okay, so here whatever I have drawn, so this result is valid even in 2D or 3D. So you can use this result even for 2D also. Yes. Then now the next one is the Stokes theorem. So actually the Gauss divergence theorem we will be using very extensively. The Stokes theorem not so much. Okay, in terms of application. Of course, it's a useful result, but for our purposes, we'll be using the Gauss divergence theorem more often. So Stokes theorem, just state it though. Anyway, Stokes theorem. So if C is a contour, so suppose you imagine that C is some contour, okay, and this S is the surface corresponding to that. So basically S is the surface which is enclosed by this contour C. So you can imagine that you have a tennis ball and you are cutting it, let us say at the equator, right? So that cut portion here is that contour, and the surface of that ball is the S here in that case. So then now you will get that u dot dx over C. So this is a contour integral over this particular contour, that is equal to integral of del cross u dot n times ds over s. So this is the Stokes theorem. So remember that this is a contour integral. So this is a integration over this contour C, and that can be converted to a surface integral. So that is del cross u, which is the curl of u dot n times ds. Similarly, you also have another result, which is u cross dx over C is equal to integral of del dot u times n minus del u transpose n times ds over s. This is also another result. As I said that these results, I mean, although they are useful, but maybe not so useful for our purposes. We will be using the Gauss divergence theorem more often than this. Fine. Then we will also mention certain theorems known as potential theorems. So potential theorems in the sense that will say that if suppose some condition is satisfied, then there exists a potential such that one particular tensor or vector is equal to, let's say, the gradient of that potential or something like that. So let us try to give representations for so this potential theorem. So this potential word is because it's like a potential function, so that exists. So so let us so as I said, I will just mention these results without proving those results, but the proofs are there in the book in case you are interested. So let V be a simply connected region, and let U be equal to del phi, then del cross U is equal to 0. Conversely, if del cross U is equal to 0, then there exists a scalar potential, phi such that U is equal to del phi. So if you have that U is equal to del phi, then showing that del cross U is equal to 0 is just trivial exercise in initial notation. Okay, so that one can prove very easily. Just use the properties of the alternate tensor epsilon I j k, rename I to j, j to k, all that kind of stuff, and then you can easily show that del cross u is equal to 0. But converse is not so easy to prove. So as I said that I am not going to give the proofs. You can take a look at the book for the proofs here. But conversely, if del cross u is 0, then there exists a scalar potential phi such that u is equal to del phi here. Right. So we can use this particular result now to show the next result here. So the next result is if T is a tensor field, such that del cross T is equal to 0, then there exists a vector field U such that T is equal to del U. Fine, so how does one show this now? So we will use the previous result in order to show this particular result. So we'll use first the definition of a curl. So this is the curl of a second order tensor. So we'll use that definition. So the definition, if you recall, was that del cross T transpose W is equal to del cross T times W. Okay. So this W, so W is a constant vector. So this is very important. If you recall, W was a constant vector, and then this was the definition for the curl of a second order tensor. So now in this particular case, your del cross T is 0. So this right hand side will go to 0 here. So you will have that this is equal to 0. And then, so now we have del cross some vector u is equal to 0. So from the previous result, if del cross u is equal to 0, then there exists a potential such that u is equal to del phi. So this T transpose W is equal to del phi because of this particular result. So, so this implies now that there exists a scalar field phi, such that T transpose W is equal to del phi. Right. And then we can write that from this we can write that T we can write as W dyadic del phi. Okay. So as I said, we are just interested in existence here. So if I construct it, maybe this may not be a unique way of doing this, but it serves our purpose. So what all we are trying to say is that there exists such a function. So here, if I take this T transpose W to be del phi, then I get this T is equal to this one, and this I can now write as del of phi W. See, because this follows because W is a constant vector. So that was very important. So W dyadic del phi I can write as del of phi W, and then this I can call as U now. So the U vector you define as phi W. So let now U be equal to phi times W, and then I get that there exists whatever is written here. So there exists a vector field U such that T is equal to del U. So that proves this particular result here. Fine. Now the next result. So actually these results will be useful when we discuss the compatibility conditions in linear elasticity. So actually all these results will play a very key role when we show that. So basically the compatibility result will be like a del cross epsilon equal to 0. Okay, so from that we will show that there exists a displacement vector u such that epsilon is equal to half of del u plus del u transpose. So that will come at a later stage, but I am just trying to tell you that where we are going to use all these theorems that we are writing right now here. So third result now is if T is a tensor field such that del cross T is equal to 0, and in addition if trace of T is equal to 0, so T is equal to 0, then there exists W belonging to skew such that T is equal to del cross W. So we can write T basically as a curl of a skew symmetric tensor. Okay, so let us prove this. So proof of this. So we have already shown that if T is a tensor field such that del cross T is equal to 0, then there exists a U, vector U, such that T is equal to del U. Right? So, from previous result, there exists U such that T is equal to del U. Right? And now we have said that in addition, trace of T is equal to 0. So trace of T is equal to del dot U is equal to 0. Okay, so this is the constraint that we are putting on this one here. Right, now let W belonging to or let W transpose belonging to skew be the skew symmetric tensor, whose axial vector is U. Okay, so so we have one result which is del cross W is equal to del dot W times identity minus del W. Okay. So this result holds for any skew symmetric tensor. So what we will do is that we will apply it now for the case of this W transpose here. So I will just replace this by W transpose, and now we for this now U is the axial vector and del dot U is equal to 0. So this is equal to 0, and then here you will have del U minus del. So we have now that this del cross W transpose can be also written as minus del cross W. Correct? So we have that del U is equal to del cross W. So this implies now that del U is equal to del cross W. Right? And that is what we wanted to show here, right? That there exists W belonging to skew such that T is equal to del cross W. Because we have already said that T is equal to del U, and now we have shown that del U is del cross W. So that is now we have got the desired result here, that it is the curl of a skew symmetric tensor here. Yes. Okay, so we move on now to the next result. So as I said, that this will be used when we prove the compatibility conditions for a linear strain field, linear strain displacement relation. Alright, so okay, now the next theorem is also a very, very useful result. So this is the localization theorem, theorem. So let phi be a continuous scalar vector or tensor field on V on some volume, then if integral of phi times dV over V is equal to 0 for all V, okay, then this implies that phi is equal to 0. Okay. So this for all v is very, very important. Okay. So that means, so suppose let us just take one example. So suppose if this is if you take this as your v and then suppose phi of dv is 0, then next time you can take some other set v or you can take it as a subset of this, or you can take it as a superset of this. So basically we are saying that for any arbitrary v, we have this integral of phi dv is equal to 0, then that implies that phi is equal to 0. So just to give an analogy here with the 1D case, so suppose suppose if you imagine, so this result will definitely not hold for one specific choice of v. So for example, the sine function, right? If you integrate it from 0 to 2 pi, then the integral is 0, but the sine function itself is not 0. So here, what is important is that now you can think that it is 0 for all v. So suppose if I choose this particular interval as my v, instead of initially I was taking it from 0 to 2 pi, but now suppose if I take some subpart, then you can see that it has to go to 0, right? And then I will now, suppose if it is non-zero here, then I will choose this as my next v, and then again it has to be 0, and so on. So wherever it is either fully positive or fully negative, I will choose that as my v. Then the function has to go to 0 in order for the integral to go to 0, and so on. And so finally you will get that the function is 0. This is just, I'm just trying to give a pictorial representation of what is happening in this particular theorem here. Anyway, so that sort of completes the first chapter on tensor analysis. We will now start with kinematics. Okay, so this tensor part is something that we will use in all the subsequent chapters, but right now we will start our study of continuum mechanics now with kinematics. So kinematics refers to something which is just obtained from geometrical consideration. So we are not going to consider the forces that are acting on the continuum and so on. So just whatever is obtained from purely geometrical considerations, that will fall under this particular category of kinematics. So that is called as kinematics. So for example, like even in your undergraduate studies, you must have studied that a strain, right? Normal strain is a change in length per unit length. So that is just a purely geometrical concept, right? We are not bringing in any forces or things like that. Similarly, something like a velocity gradient, right? That's just a gradient of the velocity, how the velocity is varying from point to point, and then we are taking a limit to get the gradient at a particular point. So it doesn't involve any forces or how the continuum behaves under the action of forces. So just whatever is obtained from geometrical considerations, that we will call as kinematics. So that is something, that is the first thing that we will study. So kinematics, all the geometrical considerations. So we'll consider now a body. So this is let's call it as E1, E2, E3. So let's take a body which is in some initial configuration, and now you are applying some forces to this body, and then it goes to some it deforms, let us say, and whatever was its original position vector at some point, let's say the position vector of some point within the initial configuration was capital X, then that goes that is mapped into a new position vector, that is, let us call it as small x here. So this so I'll call this as the initial configuration. So this I will call as the initial configuration or reference configuration also. So I'll use these terms, also a reference or initial configuration, and this is the deformed configuration. Deformed configuration. So just to give an example, if you take a cantilever beam, suppose something like this, so this is, and then you apply some loading on this, and then it goes into some deformed shape. So you can think about this as the deformed configuration. So actually the concept of a configuration need not be just a solid body. It can even be a blob of fluid that is deforming. But the only thing is that you have to take the same set of particles as they are evolving. So here, for example, I could have considered some region, this part of the cantilever beam, which is now going and deforming into this particular deform. So this you can take as the initial configuration, and this would be the deformed configuration. So it need not be the entire body. It can be some set of particles, and then as they evolve, we get to the deformed configuration here. This difference between the initial position and the final position we call as the displacement vector here. So this u is nothing but the displacement vector. Yeah? Displacement vector, and that is just the difference. So you will get that x is equal to capital X plus u. So that is just the difference between the final position and the original position. So actually, suppose if some particle goes and travels around the circle and then comes back to the same position, right? Then the displacement is just taken as 0. So although it has traveled, this distance around the circumference of a circle, but if it comes back to the same point, then the displacement is just the final position minus the initial position. So that the displacement is just taken as 0 in this particular case. Right. Now these x, capital X, are known as the material coordinates. So this x are known as, so this is just some terminology which I will use very often. So this is known as the material coordinates, and the small x are known as the spatial coordinates. Yes. Okay, and we say that there is a one-to-one mapping that takes capital X to small x. Okay, so we'll assume that there is a one-to-one mapping. So x is equal to chi of x comma t. So this chi mapping is one-to-one. Okay, so we assume this chi to be one-to-one. To be 1 to 1 map. So what the implication of that one-to-one mapping is that suppose if you have two different particles in the, so suppose if this is your reference configuration and this is your deformed configuration, then what we are saying is that two different points cannot go and occupy the same point in space, right? So these are two different points here, x1 and x2. They cannot go and occupy the same point, right? So this case is ruled out. Or the other possibility is that suppose if there is a point in the reference configuration, it cannot go and occupy two different points. So this is the other case. So we do not allow even this particular case, that there is some point here that goes splits and then let us say that goes and occupies now two different points in the deformed configuration here. So actually, I mean, strictly speaking, we have to assume that these points x are within the body. See, for example, if you take a rubber bar, for example, and consider, so suppose this is the rubber bar that you consider, and now there are 2 points that are lying here, then you now think that you are bending the bar, okay, and making it into a circle. Now, so these 2 points are now coming and occupying the same position. So, so actually this one-to-one mapping need not hold when you are considering points on the surface, and then if you are considering a deformation where you are bending it and then letting the surfaces touch at the point. So in those cases this one-to-one can get violated. But as I said, that we will consider only points within the domain, and then at least this one-to-one will hold. Then once we assume that this one-to-one mapping holds, then we can invert this, because it's a one-to-one map. We can invert this particular relation, and that inverse mapping I will call as chi inverse. So x now is equal to chi inverse of x comma t. So I can either express the small x in terms of capital X comma t, or I can express using the inverse map. I can express capital X in terms of small x comma t here in this particular case. Yes. Fine. So again, going to some new terminology now. Let us define certain terms here. Yes, so formulation in terms of capital X is known as a Lagrangian formulation. Lagrangian formulation. And the formulation in terms of small x is known as an Eulerian formulation. Eulerian formulation. So of course these names are after Lagrange and Euler, who were both applied mathematicians. So in that era, applied mathematicians would also do a lot of mechanics, and so they did very pioneering work in setting up all the axioms of deformable body mechanics as we know of today. Yes, so this Lagrangian formulation is preferred in the case of solid. Typically, I mean, that is just so for solids, typically Lagrangian is preferred. Lagrangian is preferred. And in the case of fluids, typically Eulerian is preferred. Eulerian is preferred. See, actually both these formulations are completely equivalent. In the mathematically speaking, they are completely equivalent, because it's just that instead of expressing something in terms of small x, we can always express it in terms of capital X, and then the Eulerian formulation would become a Lagrangian formulation. So we can always go back and forth between a Lagrangian and Eulerian formulation. So when I say preferred, that is just preference. It is not that we cannot use Eulerian for a solids. So even an Eulerian also can be used, but typically what happens is that in solid mechanics, you know what the, so suppose if I take a cantilever beam again, example, whatever I already considered, see, you know what the reference configuration is typically in a solid mechanics problem, and then you are applying some force, and then now you are going to some deformed configuration. So the reference configuration is known, and so typically setting up the boundary value problem or initial boundary value problem on the reference configuration is easy in the case of solid mechanics, because we know what the configuration was before the application of forces. But in fluid mechanics, typically what happens is that so maybe like we are studying, let's say, flow in a channel or something like that, and then the water or the fluid is coming from some overhead tank or somewhere, and we do not know typically what the x is, right? So if you take some typical particle of fluid, we do not know what the original position of that fluid particle is. And so in the case of fluids, typically we are studying something within some space, fixed space like a control volume or something like that. And so we know what the deformed configuration of that fluid is typically, so but not from where that particle started, right? So that is the reason that we typically prefer the Eulerian formulation when we are looking at fluid mechanics problems. Of course, as I said, that there are exceptions to this rule. So let me give one exception. So suppose if you are having water in a bucket, correct, and then now so suppose this is a water in a bucket, and now you are just shaking this bucket, and then now the water will slosh, right? So it will slosh inside the bucket. So in this particular case, actually the Lagrangian formulation also can be used, because now in this case you know that the water was, let us say, stationary before I started moving the bucket. Let's say that I know that the water is stationary. So in this case I know what the reference configuration was before I started the motion. So in problems like sloshing, maybe the Lagrangian formulation also would be a valid formulation. So as I said, that this is just a question of preference. There is nothing like right and wrong. Both are equally correct, but it's just a matter of preference. That for solids, typically we'll prefer the Lagrangian formulation, while in the case of fluids, we'll typically prefer the Eulerian formulation here. But anyway, that's, as I said, that is just a matter of preference, but there is no hard and fast rule as to which is better or anything like that. Yes. So now we will define one key quantity which will play a very, very fundamental role throughout continuum mechanics. Okay, so actually this quantity that I am going to define does not play such a key role when we are doing linear elasticity. Okay, but at least in continuum mechanics, it's the key quantity. Okay, so that's probably the most fundamental quantity that we will use again and again, and that is known as the deformation gradient. Okay, so this so I will define. So now define this f as a deformation gradient. So colon equal to, again I will use this symbol colon equal to indicate that it is a gradient. So this is the gradient of the chi map. So if you recall, we had defined your x as your chi map of x comma t. Right? So basically it is the gradient of this mapping chi with respect to x, capital X. So see, sometimes our gradients will be with respect to the material coordinates, capital X, and sometimes our gradients will be with respect to the spatial position, small x. And so it can get confusing about whether if I simply write a del symbol, it can be confusing about whether the gradient is with respect to small x or with respect to capital X. So what I will do is that always I will put this subscript here on the del symbol to indicate that whether the gradient is with respect to the material coordinates or with respect to the spatial coordinates. So in this particular case, the gradient is with respect to the material coordinates, capital X here. And so this is just the, as I said, this is just the gradient of the deformation here, chi. So in initial notation, Fij will be equal to del chi I by del xj. And so if I write the matrix, so that will be equal to del chi 1 by del x1, del chi 1 by del x2, del chi 1 by del x3, del chi 2 by del x1, del chi 2 by del x2, del chi 2 by del x3, del chi 3 by del x1, del chi 3 by del x2, del chi 3 by del x3. Right? So this is a 3 by 3 matrix, not necessarily symmetric. Okay, so so not necessarily symmetric. We'll just state that here, not necessarily symmetric. So in general, unsymmetric. Yes, and yes, and then we make one assumption on this deformation gradient. So we assume. That det f is not equal to 0. So det f greater than 0. So this is an assumption that we'll make. So let us call this det f. So let j. So I'll just define this as det f. So basically we are saying that j is greater than 0. So this is the assumption that we will make. So this is known as the orientation preserving condition. Orientation preserving condition. Okay. So yes. So this. So where does this come from? Okay. So this is based on physics. It's not a purely mathematical condition. It is based on the physics. So here you think about it that at t equal to 0, right? And so this is so let's say this is t and this is your j. So at t equal to 0, at t equal to 0, your small x is equal to capital X, and so your deformation gradient is nothing but the identity, because the u is 0. So the gradient of u is also 0. So you have f is equal to identity at time t equal to 0. So this implies that j is equal to 1. So at time t equal to 0, j is 1. Okay. Then now, in order for it to become 0, right? If it has to become negative, for example, then it has to cross 0. But at a later stage, we will show that the volume element, that dV, if dV is a volume element in the deformed configuration, then that is related to the volume element in the undeformed configuration or the reference configuration through this j. So this is dV is equal to j times dV naught. Now, if j becomes 0, right, in order for j to become negative, it has to cross 0. And if it becomes 0, then dV becomes 0. So, physically speaking, we do not allow that the volume to be annihilated, right? So because we are not allowing this volume to be annihilated, so that is the reason that we say that det f always remains positive, because it starts from 1 and it's a continuous function, so it cannot jump to the negative side without crossing 0, and it cannot become 0 because dV would become 0. So basically we are saying that det f always remains positive. Okay, so this is also known as an orientation preserving condition. So imagine that there are a set of axes that are embedded. So suppose if this is the body and there are these 3 set of axes that are embedded in this particular domain, right? And now you imagine that the body is deforming. So suppose let me just draw, let's say, a square, and then there are some axes, and now this body deforms. Okay, so now and then these axes, you can think of that they are embedded inside the body. Then those axes would also deform along with the body. And then, so what this orientation preserving condition essentially says is that a right-handed coordinate system remains a right-handed coordinate system. It doesn't become a left-handed coordinate system, or it doesn't become a reflection of the original coordinate system. And so that is the reason that your j always remains greater than 0. And this is, as I said, the orientation. So the right-handed remaining a right-handed, so that means the orientation is preserved, and so that is why we also call this as an orientation preserving condition here. Right. So as I already said, this f is going to play a very, very key role throughout our study of continuum mechanics here. Yes. So once I define my f, I can also define f inverse in terms of the inverse map. So f inverse I can define f inverse ij, f inverse of ij I can define as del chi inverse I by del xj. So now this gradient is with respect to small x. So why is it that f inverse has these particular components? So we can easily verify that f times f inverse is equal to identity tensor, right? So that is our basic definition of an inverse. So you can easily verify that f times f inverse is the identity tensor. So just use the chain rule. So del chi by del xj times del xj by del xk, that will give you delta ik. So you can easily verify that f times f inverse is the identity tensor if you use this. Fine, then let's go to the next thing. Next is what is the relation between the deformation gradient and the displacement gradient. So let us look at that. So f now is equal to I plus del u. So let us show this particular relation here. So this is the relation between the deformation gradient and the displacement gradient here. So this is obtained simply from the relation that x is equal to chi of x comma t is equal to capital X plus u. So if I take the gradient of this, so del chi I by del xj is equal to del xi by del xj plus del ui by del xj. And then this here is nothing but delta ij. So this is equal to delta ij plus del ui by del xj. So if you convert this component form to the tensor form, then you will get that f is equal to, so this is nothing but the identity tensor component, so you will get identity plus del u. So this is the relation between the deformation gradient and the displacement gradient here. Right, and I have already seen that at time t equal to 0, your displacement itself is 0, so f will be equal to identity, right? So at t equal to 0, you will get that f is equal to the identity tensor. And you can also, it is also possible to decompose this f into Ru, correct? So we have already seen the polar decomposition. So we can always write f as equal to Ru, which is also equal to Vr. And so we can decompose it into this. So this u is known as the right stretch tensor here, right stretch tensor, and the v is known as the left stretch tensor. So these are some of the terminologies that we use. But of course here you have to be a bit careful because f is not a constant, right? So f actually varies from point to point, right? So this is your capital X, so f at this point will be different than the f at this particular point. So your r and u will also depend on capital X, right? So as you keep on changing from one point to other, the r will also change to a different set of r and u and different v also at some other point here. Yeah, so using now this particular setup, we are now in a position to define now various kinds of measures such as the strain measure and so on and so forth. So let us start on that now. So so we will consider length elements, area elements and volume elements. So length, L-E-N-G-T-H, area and volume elements, right? So these are the three things that we will consider. So the length element, so we'll start with the length element. So length element. So how does length element transform, okay, from the reference configuration to the deformed configuration? So what do we mean first of all by a length element? So here, suppose if this is your reference configuration, configuration, and it goes into some deformed configuration now. So this is the deformed configuration, and suppose if you think of some curve, right, and then that is getting deformed to, so all these particles now are getting deformed to this particular curve here. And so if you take now some element here, d capital X, then that is getting deformed to an element dx in the deformed configuration. So along that same curve, right, whatever was the dx along that, remember this is a vector element, okay, so it has three components, so that is d capital X1, d capital X2, d capital X3, that is getting deformed to d x1, dx2, dx3. So this is a vector here, vector element, and the relation between these two is given by, so let me just write this relation using the chain rule. So dxi, suppose if I write, so remember that x is equal to chi of x comma t, right? So I can write this dxi as del chi I by del xj times dxj, right? So this is the relation between the differentials. So here, okay, so what happens to the time? So temporarily we are assuming that the time is not varying. Okay, so later on we will also talk about how the when we define velocity and acceleration, then we will account for the changes with respect to time. Here we are simply interested in defining a strain measure. So that means like a change in length per unit length, and so at this particular stage we will just assume that time is frozen, just like a fixed parameter here. And so this chain rule, when we are using that, we are just taking the derivatives, partial derivative with respect to capital X here. Another thing to remember is that this is an exact representation. So this is not, so what you have to remember is this is not like some delta x. Okay, so delta x is typically some finite length. This is not a finite length. This is an infinitesimal quantity. This is exactly like when you write, for example, integral of sine x dx, right? This dx is that infinitesimal quantity, right? So this dx is exactly like that dx. So in that sense, this relation is an exact relation. So you should not think about this relation as only the first order term in some Taylor series. So as I said, that when you take when you are considering the differentials, actually this is an exact relation. And so you can now write this in vector form as dx is equal to f times dx, right? Because del chi I by del xj, so this is your chi I map, and so del chi I by del xj is nothing but the deformation gradient here. And because we have assumed that f is invertible, we can also write dx as equal to f inverse times dx. So because see, we have already said that our j is greater than 0, right? So if your determinant is greater than 0, then f is invertible, and so always, so throughout the course, actually now I will always assume that whenever we are talking of the deformation gradient, we will always assume that it is invertible. We will not keep on saying that, oh, j is greater than 0, hence it is invertible. So once and for all, we will assume that f is invertible. So there is no problem in writing f inverse. So I can always write now d of capital X as f inverse times dx. So we will use now, so in the next class we will use these relations, the dx equal to f dx and dx equal to f inverse dx, to define strain measures now. So basically, as I said, the intuitive understanding behind a strain measure is like a change in length per unit length, right? So, but see, when you are talking in terms of, now we are trying to define it more rigorously, right? Because change in length per unit length, because there can be a change in orientation and so on and so forth. So it is very difficult to extend that verbal concept to a mathematical definition. So here we will try to give a more mathematically precise definition of what we mean by a strain. So to define exactly change in length per unit length is difficult. So we will use instead a change in length square. So that we will see in the next class, and so that will be used to define various kinds of strain measures, which we will do in the next class.